Electronics with Keith. Stay connected.
Okay, g'day guys. So I'm just going to show you how to install Multisim analog devices, National Instruments version 10. So this is an older version, but I find it works on Windows XP or right up to Windows 10, and I'm installing it on Windows 10. So hopefully it doesn't wreck my existing install. So just follow the instructions there. It will self-extracting zip file. So it'll just unzip the install files. Now you should be able to download the install files. I've set them up in one of your classrooms for you. It'll pop up with this window and then just say install National Instruments Analog Devices Edition. So just click on that and install. It's just like any software. Once you install it, there you go. You can choose your installation directory. So I put all my work stuff on D drive and accept the agreement, and then just allow it to install. It won't take too long, depending on the speed of your computer and so on. So once it's installed, it'll pop up, and with this window, then you just got to click on finished, and then you're done. Alright, so you should find the install file in the National Instruments directory folder. I've already got it on my start menu here, but you should find it under National Instruments Multisim Analog Devices Edition. And when it starts up, it'll look like this. You've got a blank canvas. This is where you're going to be drawing your circuits and so on. I'll show you an example. This is sort of thing that we can do, and in the next presentation I'll show you how to add components. This is a boost controller from electromagnetic devices and circuits. So we'll be able to see these types of circuits. You can hook up multimeters, oscilloscopes and so on, just basic stuff to get us started. And then when you run the project, you can take measurements. I've got a multimeter measuring the output voltage of this controller here. So when I run it, I can click on the multimeter. It's set up to measure AC, volts, and volts DC in this case, and you can measure the output voltage. Okay, so that's it. So more next time. See you later.
Electronics with Keith. Stay connected. Electronics with Keith. Stay connected. G'day guys. Alright, so I'm assuming that you've got the software installed, Multisim Analog Devices Edition version 10. So you can just going to show you a few of the tips and tricks to get you started at the very beginning. So if you look here, you can change the grid, turn the grid on and off, and you can view and show your different toolbars. If one of your toolbars disappears or something, you'll be able to find it again. Okay, so let's say we want to create a circuit, something like this, just two resistors and a power supply, something very basic. So there's a quick menu up the top here, which you can add components and so on from. So over there, so that's the quick draw menu to be able to find different things. But the best way to get started is to go to up the top, place component, and then you'll get a library of all the components available. Now, Analog Devices Edition has a limited number of components, mainly just analog device ICs and so on, but for basic components, etc., then it's more than enough. So I'm just going to search for a power supply under power sources. Alright, and then so I've placed my power supply. You can use the mouse wheel to move in and out. Place it in the rough position where you want to have it. Let's say I want to make this a 9-volt power supply. I just double click on it and I could replace it with another type or something, or I can change the supply to 9 volts. So most of the circuits that I give you, I operate them on 9 volts. So that way, if you build it at home, you can use a 9-volt battery as your power supply. So that's why most of the stuff I do is in 9 volts. Okay, so, but sometimes 5. All right, then we need a ground. Every circuit's going to need a ground. So just part of the software needs that ground in there for its calculations. Remember, this isn't just a simulation. It's not an actual circuit. It's like a mathematical calculation of what the circuit, it's a model of what the circuit will do. Okay, so then we've got a resistor. We're going to place a resistor. So I'm going to place one there and another one just below it. So two 1K resistors. You can double click on them to change the value. At the moment, I'm just going to right click and rotate it 90 degrees so they're heading the right direction, so it looks nice and neat. Okay, so I've got both resistors there set up, and so when I'm doing a circuit, I lay out all the components first. Get all the components, put them on the screen, and then I just click on the lead of a component, and then click, and then click back on the component, and I've drawn my first wire. Okay, then I'm going to connect the two resistors, so I just click on the end, and I can't join onto another end of a resistor. It has to go to an open end. You can't have more than one thing connected to one end. And then I'm going to draw that cable across there, and you'll notice that they're numbered via the order that I put them in. Right, so that's cable number 1 because I drew that first. You can change the numbers and so on in a minute. Another handy thing is you can change the colors. If you're not sure a component's connected, you can drag it to see if it is connected. That's handy. And then we can, this cable here, I can change the color of it. So that's handy later on if you're looking at it at a trace on an oscilloscope or something. You can change the color of the cable, so each trace will be a different color. That's handy. So I'm just going to change that back to red. No dramas. All right, this bottom one, I'll make this a different color. I'll make it blue or something, so I know that's the common. So there's the common. So there's my circuit. Looks all right. Okay, so just you can rearrange things, drag the cables around, just check that everything's connected. Most of the time, if you get an error, you can zoom in and out to make sure things are connected. If you try and run your projects, I'm just running it now, so the circuit powers up. If you don't get any errors or convergence errors or anything, then it should be okay. Now this is great. We can't see anything happening though. So what we're going to do is we're going to add something from the instrumentation panel, which is on the right hand side. So I've zoomed in here so you can see. I'm going to use the top one, which is a multimeter. And I'm going to connect the multimeter across this bottom resistor, just so I can measure that voltage. So I connect the multimeter up. Then if you double click on the multimeter, you'll zoom in on the controls for the multimeter. Right, by default it comes up as volts DC. So we're measuring volts DC in this case, but you can change it to an ammeter or AC meter or whatever you need to do. Don't make that an ammeter because that would short out that resistor. Alright, so you should know that from DC circuits, hopefully. And now when I run the project, so now it's powered up, I can double click on the meter and see what voltage I measure. So with your vast knowledge, you should know that 9 volts divided by 2 is 4.5. We've got a simple voltage divided the voltage in 2, so we've got 4.5 volts there. Hooray! Alright, so that's basically it. We're going to add some more meters to it later on. I'll show you in the next video how to add an ammeter and a few more tricks, and we'll end up with a circuit something like this. Right, it's a few things we can do, and then we'll start adding some active components and so on. So any of these types of circuits that we're doing here, any of your projects in DC circuits, AC circuits, some electronic subjects and so on, anything you do in class, you should be able to do in this Multisim. Okay, so that's it. Bye for now. Stay tuned for the next one. We add some more meters and a few more tips and tricks. Catch you later.
Electronics with Keith. Stay connected. Electronics with Keith. Stay connected.
Okay, g'day guys. Number 3 of our short and sweet videos on how to use Multisim. Last video, number 2, if you go back and have a look at that, we came up with this circuit, just a simple voltage divider, and we measured the voltage. We got out a multimeter from the instrumentation menu up the top right hand corner. So that's a picture of a real multimeter. In Multisim it looks like that little symbol there. So you're not going to see that actual symbol here. But anyway, so there's the multimeter, and we measured the voltage across that resistor. Alright, so what we're going to look at now is how we can add another meter and just measure the current through the circuit. So we'll have 2 meters connected up. We don't need 2 meters in real life, but we can use as many meters as we want in Multisim. So if I just grab another meter there, right, you can't stick it directly into the circuit. It's going to cause you a few dramas. So what you need to do is delete that cable, cut the cable, insert the multimeter in series with the circuit. All right. Then set the multimeter up to read, get the other actual one out of the way, right? Amps DC. Same way you would with the multimeter in real life. Make sure it's on amps DC connected in series and the other one's on volts DC connected in parallel. Alright, so then when we run the circuit, we can measure the current and you can see the voltage and current. If you did your calculations, you should be able to work out the correct values, and the values here should match what you've calculated. Alright, so then we can stop the simulation. Anytime you make any changes to the circuit, you've got to stop the simulation. Alright, make sure it's not running. So let's say, for example, we want to change the value of that resistor. Alright, so you can just double click on a component and you can change its value or replace it with another component. So in this case, we're going to change it to a 2.7k resistor. You can pause the video there and work out what the actual voltage across R2 would be from that formula. VR2, the one you want, over the lot. That's how you calculate it. The ratio of the 2.7k to the 1k. And you can see that voltage there now has increased, right? Because it's proportionally larger than the 1k. Right, so stop the simulation. You can make some changes again. Let's say, for example, we wanted to add another multimeter to measure the voltage across R1 at the same time. Alright, so I'll just get this multimeter out of the way, tidy it up, move those cables out of the way, and then I'm going to place another multimeter. Alright, from the menu on the right hand side, connect the red lead there, the black lead there, and then we can set up that multimeter to read volts DC. By default it's on volts DC already. We can run the simulation and we can measure the voltage across both resistors. Alright, so the sum of those two voltages should add up to the 9 volts. Alright, so that's easy. So we can add as many multimeters as you want around the circuit. Alright, and then you can change them or whatever you want to do. So let's say, for example, we wanted to change that component to something else. We could replace it. Let's say we want to change it to a capacitor. So that's what a capacitor looks like in real life. We're just going to change that capacitor. We can change its value to 100 microfarads or something like that. And then we could see what's going to happen now. Alright, so put another multimeter across that and we could measure the voltage across the capacitor as it charges up. Alright, so that'll be next time. So next time we'll look at what sort of simulation settings we need to do and so on, so we can measure that voltage and we can use the oscilloscope so we can monitor the capacitor charging up there. So that'll be next. Alright, so this is video 3. We're trying to keep them short and sweet. So next time we'll look at adding the oscilloscope and so on. Catch you later. Electronics with Keith. Stay connected. Electronics with Keith. Stay connected. Okay, so this is just a brief introduction into how to use an oscilloscope in Multisim. We'll hook up an actual circuit and we'll show you what the circuit would look like in Multisim and how to use the 2 different oscilloscopes and then how that compares to the actual real circuit. Okay, so let's have a look. Okay, so we've got a basic circuit here which is just a little RC circuit. Could be anything, charging capacitor circuit and so on, but let's say we want to experiment with using the different types of oscilloscopes that we have. So I'm just going to change this supply to a DC supply, so just replace it. Voltage sources, I'll just signal voltage sources just in case I want to change the frequency, so I'll make it an AC voltage. So at the moment it's a 1 volt peak, 1 kilohertz signal. So let's make it something reasonable. So let's make it 5 volts peak. at 5 kilohertz, so I can change the value of it. So I've got a 5 volt peak, 5 kilohertz sine wave being applied to this, and I've got a 1k resistor and a 100 nanofarad capacitor. So if I run the circuit, nothing's happening. We need to be able to see, and that's the advantage of an oscilloscope, is that we can actually look inside the circuit. I can put a multimeter on there and measure the voltage across the capacitor, okay, but it doesn't really tell me the story of what that voltage looks like or anything like that. Okay, so I can measure the volts AC, and I've got 1 volt RMS across the capacitor. Okay, well, fair enough, but that doesn't really tell me anything about the phase difference or what is actually happening in the circuit. So to look inside the circuit, we need to use an oscilloscope. So on the instrumentation panel on the right hand side over here, so this side over here, that's the instrumentation panel where you get all the bits and pieces that you need. So all the instruments that you need. So the main first one we're going to look at, there's a few different oscilloscopes on there. So I think about the third one down. I'll have a look in a second. If you mouse over it, it'll tell you what type of device it is. So the first one is the ideal oscilloscope, and then we've got frequency counter, bow plotter. There's another one here. We've got a 4-channel oscilloscope if we want to look at 4 different things at once. And down the bottom here, we've got a couple of my favorites. We've got the Tektronix digital storage scope and the Agilent oscilloscope. So there's 4 options of different types of oscilloscopes. So to make things simple, I'm just going to go through 2 of them. These 2. Okay, so the ideal Multisim oscilloscope, which comes up with a screen like that, and the Tektronix oscilloscope, which is a model of a digital storage scope. So these are the 2. This is the Tektronix one, is one that you'll find on your workbench in any sort of electronics laboratory, and the digital storage scope, the other Multisim oscilloscope, you can resize this one and so on, so it's much more flexible, but it can get you into bad habits because it's an isolated oscilloscope, so you can connect the crow probes anywhere you like, whereas this digital storage scope, it only has 1 ground, so it gets you in the good habit of only connecting your ground to 1 point in the circuit, unless you've got a specially isolated oscilloscope. Okay, so more on that later when you're doing AC circuits and so on, but this is just an example of how to use these types of oscilloscopes. Okay, so let's have a look at the 2 oscilloscopes and how they function. We'll just get rid of the Tektronix one for a moment, and we'll have a look at the ideal Multisim oscilloscope. So we've got 2 channels, and we've got an external trigger. Most of the time you won't be using the external trigger, so let's just stick to using the 2 channels. Special applications, and when you're a bit more advanced, you'll learn how to use the external trigger. So with the oscilloscope, we're going to connect the crow earth to ground on the ground on the circuit, and we're going to connect channel A to across the capacitor. So at the moment we are measuring the voltage across the capacitor from this point to this point. So we're going to observe the voltage across the capacitor. Okay, now another tip that I usually do, if we've got multiple channels, what you can do is you can change the color. So if I go to segment color, I can change that to blue or something, just so the wires look different, and I can change that segment color, change that to black, so I know that that's the ground lead and that's the active lead. Probably should have chosen a more exciting color for that. Anyway, let's choose bright pink. Okay, so that pink lead is my voltage and the black lead is the ground across the capacitor. So if I run the circuit now, I've got to have a bit of an idea about what I'm looking for, and there we go. I've got a horrible looking pink line across there because our time base needs to be adjusted. Okay, so I usually reverse the trace so I can see it a bit better, and I'm going to change it to 500 microseconds per division, and let's say 1 volt per division. So now I'm looking at that waveform across there. Maybe I should go a little bit longer, go to 200 microseconds per division, or even 100 microseconds per division. Now you'll notice, hopefully if my camera is picking that up, that it's crazy, it's not triggered. Okay, so then we've got to come down and change the trigger source. So we're going to put it on auto triggering. And then you can change the voltage level. That's on normal triggering, and therefore I can change the voltage trigger level there. I can type in a value at 1 volt or 1 millivolt or whatever. Okay, so you can change your trigger level. So now at least it's flashing a bit, but it's at least steady. Okay, so we've got our waveform on there. We can pause the circuit if we want it to stop flickering, and we can resize this screen to make it larger so we can zoom in and see what the circuit is doing. Unfortunately, we can't do that with the other oscilloscope, the Tektronix one. But on the Crow itself, and most digital storage scopes will have a trace, cursor, sorry, that you can use. Right, so if I drag this across, I've got two cursors, 1 and 2, and I can measure the time from one to the other and so on. So I can look at the time between those two peaks. It says down the bottom here, T1 versus T2. Minus T2 is 200 microseconds per division, and we're on 100 microseconds per division, and the time from one peak to the next peak is 200 microseconds. So 1 over that would give us exactly 5 kilohertz. And we can measure the peak value. Okay, so if I measure that voltage, I know that I am on 1 volt per division, so it's 1.5 volts. Alright, so 1.5 volts peak, nearly 1.5, well 3 volts peak to peak. So that's the way you can use these cursors to measure between the 2 points. Right, I can measure from 0, so where it crosses 0 to where it crosses 0 again. Okay, and then T1 to T2 will give us the time, and then we can measure the voltage. So if you want to measure the peak voltage or the negative peak, it'll tell you channel A what its value is, channel B what its value is. So you can use those cursors to measure, but also you can count the number of divisions. If I put it on 2 volts per division or 500 millivolts per division, you can see it's 500, 1000, 1500 millivolts, so about 1.5 volts peak. Okay, so we've successfully measured that voltage across the capacitor. We've measured it in peak to peak. We can use a multimeter to measure in RMS, but you've got to be careful in real life because most multimeters measure RMS at about 50 Hertz. So once you start going up in frequency, they become less accurate. Okay, so that's how to use that basic oscilloscope, the ideal oscilloscope that we have in Multisim. Okay, so now I've zoomed in here. I want to try out the Tektronix oscilloscope. Alright, so I'll leave the other one connected so we can compare them both in a minute. So I'm going to grab the very bottom Tektronix digital storage scope. And the good thing is that this front panel is typical of a general storage oscilloscope, digital storage oscilloscope. This is a Tektronix particular model, but most digital storage scopes have most of these features. Some have more. Okay, so I'm going to connect up the ground to the same point. And channel 1 I will also connect up to the same point. So I'm going to measure the voltage across the capacitor again with the Tektronix digital storage scope. So I'll run the circuit, okay, and then go to the oscilloscope. We've got to turn the power on. So if I turn the power on, and there we go, we've got some sort of waveform. Now one of the nice advantages of a digital storage scope, especially if you're new to oscilloscopes, they usually have an auto set button. So if I press that auto set button up here, alright, so most of them have an auto set button or something like that. So I'm going to press the auto set button and see what it does. So give it a moment, and then there it goes. It finds the trace for us, calibrates it pretty closely for us, and so on. And you'll notice we are on 500 millivolts per division, and it looks like it's 500, 1000, 1500 millivolts, so 1.5 volts peak. Okay, so it's giving us exactly the same reading, We'll just go through some of the controls. You can change the volts per division here, okay, and you got the menu to go to channel 1 and channel 2 if you need both channels. This oscilloscope has actually got 4 channels on it, and you can see down here that it shows you that we have the ground connected, and we also have something connected to channel 1. Okay, if we hooked up channel 2, it would show us a little wire coming out of there as well, and so on. So you've got some options there. So we can also, other good things are that to use is that we can print screens. So if you press that print screen, you can print this waveform to a PDF file, hand it in with your assignments and so on. I'll try that out in a minute, just showing you all the different features, and we've got cursor control, etc. and so on. So everything you find on a normal digital storage scope is on here. Let's have a look at the cursors. We'll try the cursor menu. So up here you've got a button there which is cursor button. So if I press that, it'll give me the option to use the different cursors. Okay, so then it's over here, just like we had in the ideal scope. It's at the moment it says that it's off. So if I change that, I can measure voltage, which is vertical, or horizontal. I can measure across the screen as well. Let's measure the voltage, and then once that hit that button to turn it to voltage, you see these cursor lights turn up. So that means that these two position control knobs, now these two, are controlling the cursor position. So let's have a go at making a reading of this waveform using the cursor. So if I wind this around, you can see the cursor moving up. So I'm going to move the bottom cursor up to 0. Okay, so it's on the 0 point. So I can just wind that around. So cursor, it says the cursor is at 0 volts. All right, so cursor 1's at 0 volts. And then if I adjust cursor number 2, and you'll see if I wind it down, here it comes down. And I just want to rest it on the top of that waveform, if I can get it to adjust. Okay, there we go. Looks like it's on the top of the waveform. And it tells me delta means the difference between cursor 1 and cursor 2. It tells me that it's 1.52 volts. So that's my peak voltage. I'll just adjust the time base here to make it a little bit wider so we can see the waveform better. So I just adjusted the time base, volts per division, time per division across the screen. Let's go to change the cursor now to time, and I want to measure the horizontal distance between the length of the waveform, how long it works for, how long it takes to one full cycle. So if I move the cursor over to where it crosses 0 here, and then I get the other cursor and bring it across, so I can wind it around, and winding the mouse around until it reaches 0 again, and I can see the time difference is about 204 milliseconds, and it also measures the frequency for me. I may not be as accurate. Maybe I need to change the time base to make the waveform a little bit wider. Can't quite fit it all on the screen if I do it that way. I could measure half a wave if I wanted to. Okay, but anyway, that's how you can use those cursors to measure voltages, all right, and time base, frequency, and so on. So there's a couple of the features. We've only just barely scratched the surface. We've hooked up the oscilloscope. We use the auto set button to find the waveform, and we use the cursor to take some measurements. And that's just an introduction. There's a lot more things that we can do. Okay, so I'll show you on the actual oscilloscope to see if we get the same reading. And that's it. Okay, so just ignore what I've got on the left hand side here. I've just got the circuit here, which is, it was a 1k resistor. So I've got a 1k resistor here and a 100 nanofarad capacitor. And they are connected up to the signal generator. So the signal generator is up here. I'll just show you the signal generator. So the signal generator is set up. There's the output of the signal generator there. That's going down to it, and I've got to set it up to about 5 kilohertz. And hopefully I've already got it set to 5 volts peak. Okay, so that's the circuits. And I'm going to hook up the oscilloscope, so I'm just going to put one channel across the capacitor to measure the voltage drop. Have a look at the waveform. We could talk about phase difference and things like that, but that's to do with I'm just going to mess up the oscilloscope while we're waiting here, just so you can see that when I auto set it. So I've hooked up the oscilloscope. I'm on ×1 with the crow probe, and I'm measuring the voltage across the capacitor. So let's see if we can get it to look the same way as it does in the simulator, and vice versa. Okay, so I'm looking at the waveform across the capacitor now, and I haven't got much of a waveform there. So as I said, if I hit the auto button, it goes through a bit of a sequence, and there we go. It pops up with the waveform for us. So easy to use. But you need to know and understand how to use a cathode ray oscilloscope so that you can use a digital storage scope and all its features as well. Okay, so let's say I want to measure that. I can put the cursor on as well. I can put it on to volts, and then I can move that cursor down. You can see I'm gradually moving that particular cursor down. I don't know where my pointer is gone. Okay, so you can see that I've moved that cursor down to touch the top of it, and it's measuring the distance from that cursor to that cursor. So if I go to hit the button and just move the other cursor up, I can get a peak to peak value. It tells me it's 3.26 volts. That's the change difference between that and that. Or 1.6 volts is VA and VB is minus 1.6. I can move the cursor up. Oops, that was moving the middle, moving the ground. I can move the cursor up to the middle, just wind it around. And here we go. It's probably a coarser way to do that. But anyway, I'll just move the cursor up to the middle. There we go. So I'm measuring about 1.6 volts peak. Okay, so about 3.2 volts peak to peak. Pretty close to what we got in the simulation. Okay, so anything you can do on this oscilloscope, you can do in the simulator using the Tektronix oscilloscope, or you can use the Ideal oscilloscope. All right, and the reason there might be any differences in those values between real life and the simulator is the simulator simulates perfect components. I'll take a photo of that. Now it tells me the USB drive is installed successfully, and then I can save a picture. So I've saved a picture onto my USB, and I'll put that in the presentation for you. Okay, any other questions, please let me know. And okay, so there usually will be some discrepancy between the actual real circuit and Multisim, because Multisim uses absolutely ideal components that are the exact value. So this is meant to be a 100 nanofarad capacitor. So if I plug it into my tester here, and we'll have a look to see what the actual value is. Alright, so it's testing, if you can see that. Alright, so it's 101.6 nanofarads. Pretty close. It shouldn't have made any difference to that. Okay, so pretty close, and then the tolerance is meant to be a 1K resistor. So it may not be exactly 1K. Plug it into the right sockets there, and we'll test the resistor, and it's 984 ohms. Okay, so it's quite a bit out, about 15 ohms out. So that's why the results may differ between what you do on the bench and what happens in the simulator. Okay, so that's it. So any questions, please let me know. Catch you later. Electronics with Keith. Stay connected.